We want to consider the situation that I mentioned in the previous video, that what happens in the case where we do get a zero in the denominator, that is, this limit as x goes to a of g does equal zero. And so that's what we're going to address in this problem. So we can see here, if I were going to try to evaluate this limit, our previous example says that if I'm taking a limit as x approaches, let's say I was approaching 0 in this case, of x cubed plus 1 over x plus 1, that wouldn't be a problem because the bottom goes to 1 and the top goes to 1. And so that answer would be 1. But I do have a problem here because I can see that this bottom is going to 0 when I put a negative 1 in. But also notice the numerator is going to 0. Now, when you look at that, don't just automatically say, well, that's got to cancel out and give me 1. That doesn't, because there's a lot of stuff going on here. So we know that when you get a 0 in the denominator, that's undefined, but a 0 in the denominator typically tries to make your fraction go to infinity or negative infinity, because the denominator is getting smaller and smaller and smaller, which means, if you have like 1 over 0, something going to 0, that's giving you 1 over very small numbers. And if you divide 1 by a very small number, it's going to become a big number. And it just depends on whether this is positive or negative in the denominator. And this 0 in the numerator is trying to make the fraction 0. So they're pulling in different directions. The bottom is trying to pull this thing to infinity with the numbers you're plugging in, and the top's trying to pull it to 0. So we call this an indeterminate form, because it's not determined up front what's going to happen here. Is the one in the top going to win? Is the one in the bottom going to win? We don't know. But the fact that you get a 0 over 0 does imply that maybe I can figure out a way to get whatever's causing the zeros to cancel here. So I know that x cubed can be factored. X plus 1 is already as simplified as you can get. But as long as I factor this correctly, don't do it incorrectly, but this is a sum of cubes, so it's x cubed plus 1 cubed. I know that can be factored. It can be factored as x plus 1, and then you get x squared minus x plus 1. Now, if you're asking where that comes from, that's actually a formula. In general, this is called the sum of cubes formula. If you have a cubed plus b cubed, it will always factor as a plus b, then a squared minus a times b plus b squared. And if you have a cubed minus b cubed, there's also a difference of cubes formula. All you change is that goes to minus and that one goes to plus. Otherwise, it's the same. But you can see that when I factor this, these things cancel. And I just end up with x squared minus x plus 1. But there is an issue here. Is this and this equivalent? Are they the same thing? And the answer is no. In terms of functions, if you're looking at this function and this function, they're not the same. They're both parabolas when you graph them, except this one, because you can't plug in x equal minus 1, you get a hole in your graph at minus 1. So whatever this graph looks like, it's got a hole in the graph. Same graph, but with a hole in it. So they're not the same. They're not, even though we put equal here, they're not the same thing. We just are saying this simplifies to that, which simplifies to that. And we do use equal, kind of not being totally careful. If I want to be totally careful, I should do this once I cancel out that x plus 1. But it turns out over here for limits, the fact that there's a hole in the graph is not a problem, because we know the limit is just asking where the graph's going. So if I got a graph that has a hole in it, I'm just worried about, as I come into this value, where's the graph going? It can have a hole in it. And so I can use these exact same steps that I just went through. And I mean, certainly this is equal to the previous limit because I didn't do anything but factor. That certainly doesn't change anything. But even though I used equal here without this x not equal minus 1 here, as far as limits go, this is definitely equal because these two functions are the same, except this bottom function doesn't have a hole in it. This one does, but that still will give me the same limit. It's just saying once I go to that that next step, it sort of fills the hole in if I don't put out to the side x not equal to minus 1. And so this one then is one of our basic functions, or it's a combination of our basic functions. It's a square with a minus with a plus, so it's three things added together. And so I can just evaluate each one. This first one's going to be minus 1 squared minus a minus 1 plus 1. I can just plug in because it's one of our elementary functions, or a combination of our elementary functions. So I get 1 plus 1 plus 1. So that limit equals 3. So that's one of our first tricks. So you look to see if you get a 0 over 0. Then you try to figure out if there's a way to somehow get rid of what's causing the 0 in the bottom by using whatever's causing the 0 in the top as well. And factoring is one of our biggest tricks in mathematics. Probably 90% of the time, if you see something that factors, you should factor it. That's if you're trying to simplify it or do something with it, because that's typically the correct step. So here's another one. If I plug in 1 in the bottom, so that's going to be my first attempt. If I don't get a 0 in the bottom, I'm good, because then my quotient rule up there works. And I do get a 0 in the bottom here. Up in the top, I get 1 minus 1, that's 0. Minus 2 plus 2, that's also 0. So I get this indeterminate form with 0 over 0. And I'm going to try to factor. And in this case, I'm just going to go straight in and say this is equal to the limit as x approaches 1, because I know factoring, it's not going to change the limit at all. This has 4 terms in it. And if you remember your factoring rules, when you got 4 terms, you usually factor by grouping. So I'm going to factor in this first 2 terms, I'm going to factor an x squared out, giving me an x left over in this first one, minus 1 in the second one. And from the second 2 terms, I'm going to factor out a minus 2, leaving me an x and a minus 1 in the second 2. And then from those groups, I'm going to be able to factor out, I'll finish the bottom here in a minute, I can factor this x minus 1 out of these 2 groups. The x minus 1 comes out, because that's a common factor. What's left is x squared from the first group, minus 2 from the second group. So I can factor that by a process called factoring by grouping. And this bottom is a difference of squares. Just like we have a sum and difference of cubes, we do have a difference of squares. It factors as x minus 1, x plus 1. You may remember a squared minus b squared, a minus b, a plus b. Oops, a plus b. So I got that here. So none of this changes the limit, certainly, because all I did was rewrite these in equivalent forms. This technically changes the function when I cancel that, but it doesn't change the limit. Again, it's just this. It changes it now to this new function that doesn't have a hole in it. X squared minus 2 over x plus 1. And now you can see if I plug in that bottom, I no longer get a 0. I'm actually getting a 2. So I'm just going to go ahead and say that's equal then. 2 in the top, I get 1 minus 2, and that's going to be a minus 1. So the answer is that limit's minus 1/2. All right, let's do one more. So most of our limits that we're going to run into in calculus are going to end up with zeros in the bottom, and you can see that happens here. This time using t, the variable doesn't really matter. And in the top I get 3 minus the square root of 9, which is also 0. So I see this indeterminate 0 with 0 form. Maybe you can see there's a way to factor this, maybe not. But there is a standard trick for how to handle this issue. We can see that it's hard for me to see how to factor anything with that square root in there. And so one way to get rid of the square root is you multiply. I'm going to go ahead and rewrite this limit as t approaches 9. I've got 3 minus the square root of t, 9 minus t. You can multiply by the conjugate here to get rid of that square root. That's a standard way to get rid of square roots that you don't want. So here in the top, the whole point of doing it is if you do multiply out using the proper multiplication procedure, sometimes referred to as FOIL, you get 9. Then notice when you multiply these two together, you get a minus 3 square root of t, and then these two give you a positive 3 square root of t, which gets rid of the square root. And then you get square root of t times square root of t, that's going to be minus t. Those two square roots will go away when you multiply them together. And then down here in the bottom, there's really no reason to multiply out. Look what I've got. I have 9 minus t that showed up. So just leave it in factored form, because that's going to cancel something that's making a 0 in the bottom and something that was making a 0 in the top. So this turns into the limit as t approaches 9. All I have left is 1 over 3 plus the square root of t. And at this point, I can plug the 9 in. No issue. There's no 0 in the denominator now. Square root of 9 is 3, so I get that original limit is 1/6. So this one could have been done by factoring if you wanted. If you recognize that 9 minus t can be factored, this is really 3 squared minus the square root of t squared. So you could use a difference of squares and say that this is 3 minus the square root of t and 3 plus the square root of t, and cancel it directly. And you'll still get the same place, because once you cancel at that point, you'll get to here. So it is technically a way to do some of these by factoring, even if we're using this conjugate multiplying by conjugate. But typically we use the conjugate because it's useful in a few more areas than trying to recognize how to factor. So factoring, multiplying by conjugate, that's two ways that we have to try to manipulate a limit when we get a 0 over 0 form. We'll look at a few more ways.